Hello, I'm Dr. James Wotton of IBM Quantum, and this is the third lecture in this course on quantum computing. In the first two lectures, we have been like experimentalists, or at least a toy model of experimentalists, where we have been getting our hands on qubits. We have been poking them in various ways to see what happens, to get an understanding of what kind of states we have, how they are manipulated through gates, and how they can be used in computation. Now it's time to start being a theorist and write down a mathematical representation of the kind of states and operations that we've seen in order that we can better understand it and build up towards things like algorithms. So let's first review a couple of simple circuits we've seen so far and the behavior that we've seen in order to be able to start thinking about how to represent them using mathematics. The simplest thing we will have seen so far is the circuit which does nothing. It just takes us from the default initial state to a measurement gate which represents Z measurement, and then the result we get as an output for that is with certainty a 0. Now if we were to have something a little bit more complicated where we go into an X gate, then this takes the qubit which is destined to give us a 0 for a Z measurement and acts essentially as a NOT gate, giving us with certainty a 1. We also see examples where we have some probability of getting a 0 and some probability of getting a 1. For example, if we were to have a circuit where we were to do a Hadamard gate. Doing the Hadamard gate gives us exactly 50-50 probability of getting a 0 or a 1. Well, at least it does in theory. If you run that on a real device, noise will have an opinion as to whether you really get 50-50. Okay, so we need some way to represent these mathematically. So we need to be able to write down a state which is certain to give us a 0 if we do a Z measurement. So what are we going to call it first of all? Well, let's call it 0. How are we going to remind ourselves that this is a qubit state 0 and not the number 0 or a bit string 0? So for example, when we do vectors, we might write a little arrow on top. What is our equivalent of a little arrow on top to remind us that this is a quantum state? Well, it is to write a line on one side and an angle bracket on the other. Similarly, we can define a state destined with certainty to give us a 1 for Z measurement by having a 1 and also this weird notation. But what mathematical object are we going to use to represent these? So these are two possibilities. They are the only two possibilities because this is a quantum bit. It has to be defined as something which only has two possible states. Otherwise, it's not a quantum version of a bit. And what we found is that the best way is to represent these as vectors in a two-dimensional space where we represent each of these two states as two orthogonal vectors. So the fact that these are two completely disjoint possibilities is represented by the fact that they are orthogonal, and the fact that there are only two possibilities allowed for a quantum bit is represented by the fact that this is a two-dimensional vector space. So we can use any basis vectors we like as long as they're orthogonal, given that at this point we are defining things. So let's use the simplest ones. This is pointing along one particular direction. It's the 0 direction, and this is pointing along another direction. So these aren't directions in physical space. There's not one's pointing along that direction and one's pointing along that direction. And in fact, we're going to come across the Bloch sphere where we do kind of imagine physical space and it's going to be different. But these are actually vectors that are just abstract. And so we have one vector which represents the 0 direction and one vector that represents the 1 direction, not the band. So more generally, we can write a qubit state in terms of a general vector, and that vector can be written as an amplitude times the 0 state plus an amplitude times the 1 state. This is a linear superposition of those two states. Okay, so let's move on to a new slide where we're going to talk about the notion of a scalar product or a dot product. So when we have vectors, it is often useful to have a product of those vectors that yields a scalar. So the way we do that in quantum computing is with what's called an inner product. So let's say we've got some state psi, as we just defined it, with a couple of amplitudes A0 and A1, which we like to represent as a column vector. Well, we are going to define a dual of this, which is a row vector with the same amplitudes A0 and A1, except that they are also going to be complex conjugates. So this is a little bit of a spoiler for later when we realize that we're going to need to use complex numbers. But when we use complex numbers, then it means that when we define this, it needs to be a complex conjugate. So for real numbers, this makes no difference. But for complex numbers, it means we have to reverse the sign of the imaginary part. Hopefully, you know enough about complex numbers already that that makes complete sense. So this is a representation of the same state, but just in this dual form. So again, we need some notation to flag up that this is a quantum state, but also that it's not the same kind of quantum state that we have here, which is known as the ket form, but is instead a different dual form, which we call a bra, and we flag that up by basically doing the notation in reverse. Now, when we have a bra and a ket, we can multiply them together using standard matrix multiplication to get a scalar. So let's see this in action. This time we're just going to multiply the bra form of this state psi with the ket form. Now here I've written it in rather compact notation. This is just the way I'm writing in a bit shorter form the multiplication of this vector with this vector by matrix multiplication. And in fact, this is the origin of the entire notation. Writing things in terms of these brackets is what came before writing the vectors themselves in terms of bras and kets. And it is the word bracket that was split up to get bras and kets. So there you go. Now it should hopefully make a bit more sense, and I can stop referring to it as this weird notation. Okay, if we do this matrix multiplication, we are multiplying a row vector times a column vector. And when you do matrix multiplication, you multiply rows by columns in order to get the entries of the new matrix. So because we are multiplying just a single row by just a single column, we will get just a single scalar as a result. And that scalar is equal to, well, it's the square of the magnitude of A0 plus the square of the magnitude of A1, where here I'm using the fact that for any complex number, the complex conjugate times the original complex number is the square of the magnitude. Now let's do something which is not multiplying a bra of a particular state by the ket of the same state. So let's say we want to do the inner product of 0 with psi. Then this is multiplying this basis vector 1, 0 by our vector A0, A1. Oh, of course, I can point out this is actually the complex conjugate of the number 1, but that's just 1, so who cares? Now, if we do this, we get 1 times A0. So let's flag that up. We get 1 times A0 when we're doing this matrix multiplication times plus 0 times A1, which gives us in the end the answer A0. I'm not going through each individual step of the matrix multiplication here because it's just matrix multiplication, and this is something that there is vast resources on the internet to look up, and hopefully you already have some knowledge of matrix multiplication already, and I have to choose where I go into detail. So if that doesn't make sense, well, you know where I am to ask me questions. So here we have found that if we do the inner product of 0 and psi, then we get a 0, which is exactly the amplitude that goes in front of the 0 state in the superposition. So we get how much zeroness there is in the superposition by doing this inner product. Okay, now let's do a couple of inner products on states that we already know very well, which are the 0 state and the 1 state. So if we do the inner product of the 0 state with itself, then what we get is the following. So we do this matrix multiplication, 1 0 with 1 0, and that didn't come out a very good 0, but at least it's topologically equivalent. So this is 1 times 1 plus 0 times 0, which is 1. And similarly, when we do this with the state 1, we get, in this case, 0 times 0 plus 1 times 1. I'm giving you the answer while I'm writing it, which is slightly confusing, but it also comes out as 1. And if we do the off diagonals, so a 0 with a 1 and a 1 with a 0, then what we get is, in this case, 1 times 0 plus 0 times 1. In the other case, it's the other way around, but nevertheless, in both cases, we get a 0. So for a state with itself, we should get a 1. And we see that in both of these cases. And between two orthogonal states, we get a 0. And this is what we should find when we do the inner product of a state with itself. If it's nicely normalized, then we should get a 1. And if we take the inner product of two orthogonal states, we should get a 0. This gives us a normalization condition for our general state, that if we take this general state, we do the inner product of itself, then, as you know, we get this relation, and I'll write it out in its more, well, it's longer form. A0 star plus A0, A1 star, sorry, A0 star times A0 plus A1 star times A1. And to have this as a nicely normalized state, in the same way that the 0 and 1 are, then we want this to be 1. So writing it out in the same way I did earlier, the square of the modulus of 0, A0, and the square of the modulus of A1 should add up to 1. Right, there are some useful things to know. Now we can try and work out what the state looks like that we get from doing a Hadamard. So if we take this particular example of a quantum state, where we do a Hadamard, then we know that if we were to do a Z measurement on this, we are equally likely to get the outcome 0 or 1. Although if we were to do an X measurement, we would definitely get the outcome 0. So what does this look like in terms of a state? Well, the fact that it's equally likely to give us a 0 or a 1 means that it shouldn't be biased towards 0 or 1 in any way. So, well, the most even-handed thing would be just to have 0 plus 1, because this is no more 0 than it is 1, it's no more 1 than it is 0. But also, in order to make sure it's nicely normalized, we can add some constant there. So let's see what value that constant should take with this normalization condition. But first, let's give it a name. We are adding together 0 or 1, so let's call this thing plus. And if we do the inner product of plus with itself, then we find that the answer is 2 c squared, or more generally 2 times c star times c, because in general this could be a complex number, but let's keep it real. Sounds a bit 90s. And we find that this is therefore, because we want this to be equal to 1, it implies that the c has to be 1 over root 2. So this gives us our definition of the plus state. The plus state is 1 over root 2, 0, plus 1. Okay. Now, why does that give us equal probabilities of 0 or 1? Well, what else is it going to be giving us? It's basically an argument from symmetry. There's no reason why it would be more biased towards 0 or 1, because it's equally a superposition of the two of them. But in general, we can't use symmetry arguments to work out what the probabilities will be. So let's analyze what's going on this slide a little bit more, and we can get some clues as to what corresponds to probabilities in these states. Here we have an equation where we've got the magnitude of a complex number squared, which is itself a real number, added to another magnitude of a complex number squared, which is of course also a real number, equal to 1. And here we have two things that should be equal to a probability of half, the outcome of a 0 and the outcome of a 1, and both of them have an amplitude of 1 over root 2. So if we look at what a 0 and a 1 are for the case of the plus state, we find that these squares of amplitudes for the case of the plus state are equal to half. So they're actually equal to the probability. Now this could be a coincidence, but one thing that could lend weight to this not being a coincidence is this equation over here, where we see that in general these two numbers have to add up to 1, just like the probability of getting a 0 and the probability of getting a 1 have to add up to 1, because these are two disjoint possibilities that completely cover all possibilities. So what I'm getting at here is that from those examples, it kind of makes sense, hopefully, that the probability of getting a 0 should be the square of the amplitude for the 0 state, and the probability of getting a 1 should be the square of the amplitude for the 1 state. Now you can either be convinced by the arguments that have been used so far, or you can accept it as a rule. Either way, it's good. So this is called the Born rule, in fact. With this in mind, we can start thinking about what would happen if we did this circuit, which is to do first an X and then a Hadamard. From Hello Kids Kit or from other experimentations, what you can find is that if you were to do a Z measurement at the end of this, it would give you a 0 or 1 with equal probability. So the corresponding state, like the case of the plus state, should be some sort of equal superposition of the 0 and the 1 states. However, if you were to do an X measurement, you would be certain to get a 1 as an output, which is the complete opposite of what you get for the plus state, where you're certain to get a 0 for an output. So we have to come up with a state which is, like the plus state, an equal superposition of 0 and 1, but it should also be orthogonal to the plus state. So the way we can do this is simply to put a minus in the middle here instead of a plus. So here the amplitudes are a 0 equals 1 over root 2, which turns into the probability P0 equals half, giving us this probability of half that we get the outcome 0. But for the case of a 1 here, the amplitude A1 is minus half, which squares again to half. So the probabilities, because we're squaring them, this minus disappears. and we get to the probabilities we need. And you can verify yourself, but if you take the inner product of this state with the plus state, you'll find that they are orthogonal. So here we have a state which we call minus. It is orthogonal to the plus state, just like the 0 and 1 states are orthogonal to each other. But if you measure either of these in the z basis, you get random outcomes of 0 and 1. If you measure them in the x basis, you will get either definite 0 for the plus state, definite 1 for the minus state. And if you were to measure the 0 and 1 states in the x basis, you would get sort of similar results. You would get random results. But when you measure them, of course, in the z basis, you get these definite results of 0 and 1. So there's actually no way that the 0 and 1 states are more special than the plus and minus states. We could have started with the plus and minus states. We could have the x basis measurement as our favorite kind of measurement instead of the z basis measurement. There's no mathematical reason why one is any more important than the other, but we just have a bias towards the 0 and the 1 and the z basis when we're thinking about quantum computing. But they are not in any way more fundamental states. They are just as valid as any other superposition. Everything is a superposition of everything else. Now, because we're using complex numbers, there is the ability to define another pair of states which are orthogonal to each other, but are what we can call mutually unbiased from the other two bases. So they're the ones with the I in here. So for example, 0 plus I, 1, again, normalized 1 over root 2. Because of the possibility of having complex numbers, this is perfectly valid. And if we were to take this amplitude A1 here, which is I over root 2, then the complex conjugate of that, A star, is equal to minus I over root 2. And you multiply those two together to get the probability of A1, and you find it is half. Now this is the state which will give you a definite result when you measure in the y basis, and you can also define one that is orthogonal to it. And this gives us what happens in the y basis, but who cares about the y basis? So this is just to make sure you know that complex numbers are indeed required here, because it's required for us to incorporate the y basis in, and we already know that the y basis exists because we covered it very lightly in Hello Qiskit, not in the lecture, but in the actual Hello Qiskit workbook itself. And so this is why. So we will be needing to use complex numbers in general as we go forward. So now let's think about the general form of a quantum state. Well, one thing that we have to do before we can really nail down the general form is think about the notion of global phase. So if we imagine the state 0 and the state minus 0, then how do these differ? So 0 is a state for which the amplitude A0 is 1, and so it has a probability of getting the 0 state of 1. A0 is a state for which the amplitude is minus 1, so the probability of getting a 0 is 1. If you were to measure in the z basis, you would find no difference between these two states. So what about the x basis? Are they some way distinguishable in the x basis? So in the x basis, we can write the 0 state as the superposition, and I'll leave you to verify this for yourself, of the two basis states plus and minus. And this shows us that we get these probabilities of a half for plus and minus, because we can think of it as some amplitude, let's call it A plus for plus and A minus for minus, and these are both 1 over the square root of 2, and we can write the probability of getting a 0 in the x basis, let's call it P plus, as this square of A plus, which is half, for the minus 0 state, what happens for this state here? Well, all of those probabilities are the same because the amplitudes are multiplied by a -1, but that doesn't matter because they disappear when we take the square. So we find that actually in the x spaces as well, these two states are completely indistinguishable. And in fact, any measurement we could ever possibly make, these two states would be completely indistinguishable. There is no way to tell whether you have a 0 state or a -0 state, or even more generally, we could multiply by any complex phase with magnitude 1 and get a perfectly normalized state, which is completely indistinguishable because when we take the magnitude, this phase disappears and therefore it doesn't turn up in any of our probabilities. Now, these probabilities for measurement results are the only thing that's actually physical when we are doing anything with qubits. If our measurement results do not reflect a difference between two states, and if there is no way in theory that any measurement could distinguish between two things, then are they not the same? So this is true in this case as well. When you multiply any state by a global phase, as we call it, so this could be a factor of -1 or any factor of e to the I theta for any real theta, then the state is physically indistinguishable. So even though mathematically it might look different, physically it is indistinguishable. And therefore, when we are writing down the most general form of a quantum state, we have to bear in mind that we don't have to include the ability for any general global phase because global phases are irrelevant. So let's write down our general state again. We have our psi equals A0 plus, A0 times this basis state 0 plus A1 1 and A0 has its real part and an imaginary part, and we can write down the real part and imaginary part as two real numbers, but the imaginary part gets multiplied by I to make this a complex number. So we can think of either of these in terms of a real part and an imaginary part, which are two real numbers, but also there's a way of writing complex numbers in a polar form, again in terms of two real numbers, but in a different way. So we can have a phase and we can have the magnitude. So here is the magnitude and I'll call the phase alpha 0. So here the phase is a real number. If it's 0, then e to the I 0 is 1. So this is just a positive number. If it's pi, then we have -1. So this is a negative number. If it's anything else, it's a more general complex number. So with our complex numbers in this more general form, let's write them out. So our psi is equal to e to the I alpha naught A naught. And here I'm using naught when I'm speaking instead of 0 as I've used before, just because I can be inconsistent in what I call that particular number. I have been trying many years to be more consistent, but has yet have failed, so please bear with. So this is a general form of a superposition state, but there's a little trick we can do, which is to take that e to the I alpha naught as a global phase, and for that we have to remove it from here. And we don't actually care about it anymore because it's become a global phase. So we can get rid of that. Now it's not really true that it's equal to what we had before. So let's remove that for a moment, but it's physically equivalent. So this is what we're going to call our state psi. So let's put that equals back. Now we don't need to have alpha naught and alpha 1 both in here anymore, because it's only this difference between them, this phase difference, that's actually physically relevant. So instead of having them both, let's just have a single parameter phi. So here we have a more simple form because we've removed one of these numbers that we had before, and we've made it so that it has a consistent global phase. Now, one other thing that we can note is that since a0 squared plus a1 squared is equal to 1, these aren't really two independent parameters because they have this constraint over them. And we can actually replace these two parameters with a single parameter. And the way we can do that is using a similar relationship, which is that cos theta squared plus sine theta squared is 1, whatever the value of theta is. So another way of having a general form of these two parameters is to replace them with cos theta and sine theta for some theta. And so whatever pair of parameters, a0, the magnitude of a0 and the magnitude of a1 that we could have had before, we can replace with cos theta and sine theta. Now there's another aspect here that with particular values of theta, you can get one of them be negative and the other one be positive, so that's a phase difference. And so also this phase is doing the work of that. But yes, we can have any balance of these values that we want using cos and sine and a single parameter theta. And the reason why I've drawn the theta slightly floating here is it's actually better for us to use theta over 2 rather than just theta, and we'll see why in a moment. So our general form of a single qubit superposition state is parameterized by two numbers, theta and phi. So here's another example of something that's parameterized by two real numbers that we might like to call theta and phi, which is a point on the surface of a sphere. Using polar coordinates, we can use an angle, which is the angle down from the z-axis, as we see here, and we can use an angle around from the x-axis, as we have here, as these two parameters. And the reason why we use theta over 2 in our state is so we can do a one-to-one correspondence between states and points on the surface of this sphere. So let's look at some particular states to see this in action. The 0 state has a theta of 0 and a phi of whatever, because the phi is on the 1 state and the 1 state has no amplitude anyway. So this corresponds to the theta equals 0 state, which is at the top here with the polar bears. Now, the 1 state has a theta of pi. And so we have cos pi by 2 and sine pi by 2. And as we saw as one of the examples in the Python introduction, sine of pi by 2 is 1. So this is an example where it is this state which is relevant. And since the 1 state is the only state, the e to the I phi becomes a global phase, so we also don't care about what's going on with that. So here we have, among the penguins, the 1 state. Now the other states we have been looking at, such as plus and minus, are all on the equator, so they have theta equals pi by 2, and for phi equals 0, you are pointing along the x-axis, so that's your plus state. For phi equal to pi, then your e to the I pi is minus 1, so you have a minus here in the superposition instead of a plus. So you have the the minus state and the y-basis states are pointing along the y-axis. So this is why we call these things x measurements and y measurements and z measurements, because the two states with a definite result for the z measurement are ones that we can associate with the z-axis of this sphere. And for the x measurement, we can associate them with the x-axis. For the y measurement, we can associate them with the y-axis. So that gives us a nice sort of visual understanding of what's going on here. And it's also quite nice because we can see that orthogonal states here are antipodes on this sphere. So this isn't a two-dimensional real description of what's going on in a qubit. Well, I say real as I mean sort of true, not real in that it contains real numbers. There's just a correspondence between a two-dimensional vector space with complex numbers and a three-dimensional vector space with real numbers, which allows us to imagine this weird two-dimensional vector space with complex numbers as a nice, sensible, three-dimensional real thing that we can understand better as beings that live in a three-dimensional real valued world. So it's not the same vector space, and that's why the orthogonal states of the two-dimensional complex vector space actually correspond to antipodes in this three-dimensional version, but nevertheless it's a nice correspondence between different forms of state. And in fact we can define a measurement between any pair of antipodes on this sphere. We can define any state which is anywhere on this sphere, and we can define its antipode, and we can define a measurement which is distinguishing between these two things, assigning one of them the outcome 0, the other one the outcome 1. This visualization, I should get rid of this eraser. This visualization is also good for thinking about what the operations are that we can perform on single qubit states. So when we perform a gate, we are moving from one particular state to another, and these are both states that correspond to points on the surface of this sphere. So the surface is required because this is our normalization condition. Actually, we will see examples where they don't live on the surface, but we have to go to multiple qubits to see effects like that. So the gates that we have move things around like rotations, so we can think of them as rotations. Here I've redrawn the sphere so we can think about what some of these rotations might be. So we can have a rotation around the x-axis, for example, by some angle, which is a rotation which is going to take us around the x-axis by that angle. For example, if we were to have a rotation around the x-axis by an angle pi, this is a 180-degree rotation. So it's something which would take a 0 state and turn it into a 1 state. And it would take a 1 and rotate it round to a 0. Now that's something we've seen before. That is the X gate. So this is why the X gate is called the X gate. It's a pi rotation around the X axis. But we can have any angle of rotation, not just pi. We can also rotate around the Z axis, and that's exactly the one that is explicitly referenced in the textbook chapter that this lecture is based on. This is also a rotation around an axis, but this time in the case of the Z axis. And this will take something like a plus state over here and turn it into a minus state, and vice versa. So this is the Z that we've seen before. But also there are special names for other rotations around the Z axis. For pi by 2, we call it S, and for minus pi by 2 we use S dagger, for reasons we'll see in later lectures. And for pi by 4 we call it T, and there is also T dagger for minus pi by 4. Now, because these are operations that we apply to vectors, we can also think of them as matrices. Okay, so gates can be represented by matrices. Let's look at a few examples of that. The first gate we are going to look at is the identity gate. Now, this isn't one that we have discussed so far because it is the trivial gate. It is the gate that does nothing. So far, when we've wanted to do nothing, we've just done nothing. But if you want a gate that explicitly does nothing, this is it. So the matrix representation of the identity gate is the identity matrix, and this is the matrix which, when applied to any general vector, will give you exactly that same vector back. So let's apply the identity matrix to some vector psi, and this means that we are doing the matrix multiplication of this particular matrix with this general state with amplitudes A0 and A1. And as you should know, or as you can look up, matrix multiplication works by taking rows and multiplying them by columns. So here we're taking the 1 from this row and multiplying it by the A0 from that column, giving us A0. And then we're taking the 0 from that row and multiplying it with the A1 from the column, and of course getting 0. So we don't have to add that. When we do the other row times column, then we do this 0 times this A0, this 1 times this A1, and that gives us A1. And there we see we have done nothing. So that is the identity matrix. The X gate has a matrix representation that looks like this. So it's also multiplying things by ones and zeros and will yield quite an easy answer, just as the identity matrix does. But because those ones and zeros are the other way around, then you get the results the other way around, and explicitly you get A1 and A0. So it has the effect of flipping the bits. So when you apply an X to 0, you get a 1, and when you apply an X to 1, you get a 0. But we can also look at what happens when you apply X to some other states we know. What happens when you apply an X to plus? Well, it's still got a 1 over root 2 out the front. And of course the plus state is 0 plus 1. So that 0 is going to turn into a 1. And that 1 is going to turn into a 0. But 0 plus 1 is the same as 1 plus 0. So actually you're getting the same state out as you started with. X applied to plus does nothing. And this is what we might expect from what we saw in Hello Quantum. However, if you apply X to the minus state, then you get 1 minus 0, which is not quite the same as the minus state. In fact, if you take a global phase of -1, then you get back to the minus state. So this is the same as minus, or -1 times the minus state. So this is, since this is a global phase, it also effectively does nothing. So also we can say that the X gate does nothing to the minus state, but it does have an effect that we can take into account when superpositions happen. So this will cause a phase difference between plus and minus states within superpositions. So it's not completely that it does nothing, but it does nothing when it's applied to the minus state on its own. To see an example of this, let's move on to another gate. So the Z gate can be represented like this. It's rather like the identity matrix, except you have this phase difference between the 0 and the 1 states. So you apply this to 0, and you will get a 0, but apply this to the 1 state, and you'll get -1. So its action on the 0, 1 states is the same as the X gate action on the plus and minus states. So this means that when we apply Z to some general superposition, it will keep the 0 part as a 0, but it will multiply the 1 part by -1, giving us this. And because this phase difference is not global, you can't pull out a factor of -1 and ignore it. It is something that is actually relevant. So we can see this when we apply the z to the plus and minus states. You apply z to plus, well, what is plus but the superposition. So let's look at the effect of the z gate on the plus state. So the plus state is, of course, this superposition with amplitudes of 1 over square root of 2 with 0 and 1. Usually we would be adding the 0 and the 1, but because of the effect of the z gate, we will instead be putting a minus in here, giving us the minus state. So the z flips the plus state to a minus state, and similarly flips the minus state to a plus state, and therefore has the same effect on the z basis states as the x gate does on the 0 and 1 states. Another important gate is the Hadamard. Now this cannot be expressed purely as a rotation around the x-axis, the y-axis, or the z-axis on the Bloch sphere. It can be represented in terms of a few of these rotations combined together, but another way to think of it is as a rotation around a different axis, the one that lies equally between the x and z axes. So it is a rotation around this axis here by pi. And that is why it takes you from a 0 state round to a plus state and vice versa, and also why it transforms between plus and minus. The way we can write this down as a matrix is using a overall factor of 1 over root 2 makes it easier, and then we put in 1, 1, 1, minus 1. It's also possible to write this down as 1 over root 2 times x plus z. So if you look at the effect of h on 0, you do the matrix multiplication. I'll leave this as an exercise to the viewer. You will get a plus, and if you do it to a 1, you'll get a minus, and so it's transforming the z basis states, as we can call them, the 0 and 1 states, to the x basis states, the plus and minus states. Now another important thing to note is that these gates can also be written in terms of outer products. So let's have a look at an example of that. So let's take a ket and multiply it using matrix multiplication by a bra. In this case, we just do the bra form of the same one. We know that if we do a bra times a ket, we get a scalar. If we do a ket times a bra, we get a matrix. So here we have the ket, which is the column vector 1, 0, multiplied by the row vector 1, 0. So this is going to give us a matrix, and the element at the first row and the first column of this we get by taking the thing from the first row of this and the first column of that, which is 1 times 1, and therefore 1. To get the first row and second column, we do 1 times 0, so that's a 0. And then for the second row and first column and the second row and second column, we also get another 1 times 0 and a 0 times 0. So this is the matrix form of this particular outer product. And we can write this more succinctly as 0, 0, like that. So 0, 0 is 1, 0, 0, 0. Okay, and if we were to do 1, 1, we would get 0, 0, 0, 1. And then we can write down the identity matrix by just adding these together. The identity matrix, remember, is 1, 0, 0, 1. And therefore it can be written as 0, 0 plus 1, 1. Now let's try this with the X matrix. So we can find that if we do the off-diagonal terms, like 0, 1 and 1, 0, these give us the off-diagonal elements of the matrix. So 0, 1, for example, and I have to do this explicitly because otherwise I forget which way round they go. So this is 1, 0 times 0, 1. And so we get here a 1 only for the first row and second column. So this means that we put a 1 in here and a 0 here, here. That's supposed to be a 0, and here. And then also, if we were to do 1, 0, we would get the other off diagonal, which is a 1 down here and 0 elsewhere. So that's also supposed to be a 0. And then our X gate can be expressed like this. And you might notice something about this form in which we're expressing an X gate and a coincidence with what the X gate actually does. Because the X gate turns the 0 state into a 1 state, and here we've got a 0 and a 1. It turns a 1 state into a 0 state, and here we've got that same thing. This is actually not a coincidence, because if you were to apply this operation, so with a fresh screen, let's see what happens when we apply X to 0 in this way. Well, X is equal to this outer product of 0 and 1 and of 1 and 0. So let's see what happens when we apply each of those terms to the 0 state independently. Well, if we've got this outer product of 0 and 1, which we multiply by 0, so we're thinking of this as taking this outer product and multiplying it by this vector, but we could equally have thought of this as taking this inner product and multiplying it by this vector. And if we view it in that way, we have the state 0, which is multiplied by this inner product 1, 0, which itself is a 0, the actual number 0. So this all comes out as the actual number 0. So if we were to do the same thing with the other term, which has this outer product 1, 0, and multiply that by the 0, well then if we reinterpret this as being the inner product, this is the inner product of 0 with itself, which yields a 1, and hence we have the 1 state multiplied by the actual number 1, which is the 1 state. And so what we saw there was this term was basically looking for a 1, and if it found that 1, it would turn it into a 0. But that didn't happen, so that whole term did nothing. Whereas this term was looking for a 0, and once that 0 slotted in there, it output a 1. So we can think of the action of a gate in that way. And this means that we could also have written the effect of the X gate in a completely equivalent way, which is as the gate which turns plus into plus and minus into, well, minus. And similarly, we can write Z as one with zeros, because it turns 0 into 0 and 1 into minus 1. But we can also write this in terms of pluses and minus in a way that switches plus to minus and minus to plus. So these are some tricks that we will look into more in later lectures, but you can already start playing around with these outer products now. So now let's look at more general Z rotations in this matrix form. So if we take RZ by some angle phi, there are two ways we can write this down. We'll be thinking in this lecture in terms of the way where it looks like this matrix with an e to the I phi here. But we could actually equivalently write it down as the matrix with e to the minus I phi over 2. That's supposed to be a 2. And e to the I phi over 2. And this differs from the other form by, again, global phase. Sometimes we might choose to write it down in this latter form. Sometimes it makes more sense to do it in the other form. But we will be using this form for the moment. So if you were to put pi in here, you would get e to the I pi as minus 1. And this would recover the known result, which is 1, 0, 0, minus 1. And if we look at RZ of pi by 2, then that's what we're calling the S gate. We can also call it the square root of Z gate, and that is 1, 0, 0, I. And we can call it the square root of Z because if you were to do two of these, if you were to do an S followed by another S, so S squared, then this would be the same as a Z. And that sort of relation is actually something we'll find useful later on. So there you have some gates as matrices, and quantum computing is basically all about just playing around with these matrices, playing around with the behavior that we get as we combine them. So by looking at things like, well, what happens if you do a Hadamard and then a Z and then a Hadamard, and finding out that that gives you exactly the same as an X. Well, most of the time we'll be doing more complex things than that, but playing around with these sorts of relations is pretty much all that quantum computing is about. You just have to get to bigger and fancier implementations of it, and so that's what we'll be doing in the future lectures. But that is all for today. Thank you for listening, and I will see you next time.